Okay, welcome to Let's Get to the Marks. We're looking at the A-Level Chemistry Paper 2 Organic and Physical Chemistry exam from 2022. That's Paper 2, A-Level, not AS. And I recommend you press pause before each question, have a go at the question, and then have a go at the walkthrough, which I will go through once you unpause. Awesome. Let's go. So, question one, an acidified solution of butanone reacts with iodine as shown. We've got the equation there. Draw the displayed formula for CH3, CH2, CO, CH2I. Give the name of CH3, CH2, CO, CH2I, and the displayed formula. And it's 2 marks. So we're going to get 1 mark for the displayed formula, 1 mark for the name. So as I said before, pause it, have a go. Here's the answer. First thing we do is circle the CH3 on the structural formula that we've been given here and draw that out in displayed. So, and then we've got the CH2 next. So we put C, we display the bonds and the H2. Then we have CO. So you work through the formula piece by piece. That is known as the carbonyl group, the CO group. And then we have CH2 and with an I. And that is your displayed formula, and that will score you 1 mark. Now we want to work out how to name it. So I could number the carbons like this, 1, 2, 3, 4 from the left, but that would be wrong because we need to number the carbons that give those functional groups of the I and the carbonyl group the lowest possible number. So you do 1, 2, 3, 4 from the other side, from the right. So the name of this is 1-iodo, acknowledging the iodine atom there. Butan, because there's 4 carbons, 2-one, because it's a ketone and the carbonyl group's on the 2. Let's go. 1.2. The rate of the reaction, the rate equation for the reaction is as follows. We got it here. And then we have been given the initial concentration of CH3, CH2, CO, CH3, I2, and H+. So the question is asking us, calculate the value of the rate constant K. So we want to write out the rate equation, which I'm doing here, except for, I'm using the wrong brackets. I should be using square brackets. So that's a bit dumb of me. And essentially, this question wants us to rearrange this rate equation to find K. So calculate the value for the rate constant K and give the units. And that's worth 3 marks. So what I want to do is divide the concentration of these 2 reactants underneath rate. So rewrite it out, but move those 2 to underneath rate. Because they're multiplication on one side, you can divide both sides and move them over. So we now have rate over CH3, CH2, CO, CH3 concentration and the hydrogen ion concentration as well. And that's going to equal K. So I now need to just substitute the numbers from the data in the table into the equation and work out K. And that will score me 2 marks. So 1.45 times 10 to the minus 4, which we're told is the rate, and we're told that over here. And I now need to divide that by the concentration of CH3, CH2, CO, CH3. So I need to put 4.35 in square brackets. You always use square brackets for concentration, which I'm going to multiply by 0.285, and that is the concentration of the hydrogen ions. Notice I put a red X next to I2. It's not in the rate equation, so it doesn't appear in our equation. Okay, it doesn't affect the rate, that reactant. So, and that's going to equal 4.04 times 10 to the minus 5, and that is the value for K. Now, the units for K, we need to work out. And we can do that by writing out the units of rate, which are on the top, and that is mol dm minus 3 s minus 1, and putting that over the units for the concentration of the ketone and the hydrogen ions. So both of those have mol dm minus 3. Now, because I've got 2 mol dm minus 3s, I can just cross them out. So essentially, I'm dividing s minus 1 by mol dm minus 3, and that's going to give me mol dm minus 3 S1. So the units are mol dm to the minus 3 S minus 1, and the answer for K is 4.04 times 10 to the minus 5, and that will get you all 3 marks, which is lovely jubbly. Now, the units for K can change depending on the number of concentrations you have at the top and if they're to the power of anything. Okay, let's go. Right, we're on 1.3. Calculate the initial rate of reaction. I've just underlined it here in blue very badly, when all the initial concentrations are halved. So what would happen if we halved CH3, CH2, COCH, and the hydrogen ions, which I've circled here in orange? Well, we can find it out. We just plug the numbers in for the rate equation, and this time you don't need to rearrange it. So it's rate equals K times the concentration of each, and we're halving them, so dividing them by 2, as you can see here. And if I bing, put that in the calculator, we're going to get an answer that is 3.36 times, no, 63, sorry, 3.63 times 10 to the minus 5, and that is what the rate would equal. Check that on your calculator, make sure that is correct. Now, there is an alternative way to do this. We could instead do 1.4. We could write out the initial rate of reaction, which is 1.45 times 10 to the minus 4 mol dm to the minus 3 s minus 1. So 1.45 times 10 to the minus 4. Now, because each of the reactants are first order. Now, if you're wondering what first order means, it means they don't have a little number. Like I've just written 2 oranges there, an orange 2 on each. They don't have that. So they're not to the power of anything. They are first order. And first order have a linear relationship with the rate of reaction, first order reactants. So if I half one, it's going to half the rate of reaction. If I half the other, that will also half the rate of reaction. So I need to divide it by 2 twice, and I'll get the same answer, 3.63 times 10 to the minus 4. So you might prefer that approach. It's a bit quicker. If you spot they're both first order, then they both have the same effect on the rate of reaction. So if you half one, you divide it by 2, half the other, you divide it by 2 again. Right, moving on. Let's go, 1.4. Okay, pause the video, have a go at this one. Okay, here's the answer. Basically, when this reaction is finished, what would we observe when all the iodine has reacted? Well, iodine, when it's in solution, is brown. So when the reaction is done, we should see the color go from brown to colorless. Hope you got that right. Now, let's move on. 1.5. Describe and explain the shape of this graph. We've got rate on the left-hand side, which is represented by 1 over the time, 1 over T. S to the minus 1, and we have temperature along the bottom. Look, as the temperature increases from 20 to 45, what happens to the rate? The rate also increases. 1 over T goes up. So we can just describe that, and that's going to get us a mark. As temperature increases, 1 over T, or we can say as rate increases if we prefer. We can then say, as temperature increases, rate increases, or 1 over T increases. And then the second mark in the describe of this question is that it's not a linear relationship. So if we look at the bottom of the graph, we can see it's less steep. If we look at the top of the graph, it's getting steeper and steeper, the gradient. So the rate, the increase in rate is increasing. And we call this an exponential increase. So it's not a linear relationship, it's exponential. Okay. And now you're going to get 1 mark for explaining why is it that as temperature increases, the rate increases. And simple. More particles have the energy above the activation energy. You can write more particles carry kinetic energy, so more frequent collisions, but I'm not sure that gets you the mark. They're really interested in you saying more particles have energy above the activation energy. And that's the reason for the exponential increase in rate with temperature. And that'll get you 3 marks. 2 for the description, 1 for the explain. Right, deduce the time taken for the reaction at 35. We need to go here to 35 degrees, draw a line up to the line and a line across, and we get 0.03. Now, some students will write that as the time. That's not the time, that's the rate. That's 1 over T. So I need to write 1 over T equals 0.03. For those of you that are bad at maths, you can put this in a magic triangle. So what you can do is you can put anything that's above a divide line at the top of the triangle and the other 2 factors at the bottom. So we've got T times 0.03. And what we're going to do here is go 1 over 0.03 equals time. And if you plop that into your calculator, you'll get 33.3 seconds. So 1 over T equals 0.03. Okay, I feel like I'm talking at 90 miles an hour in my recent videos. For a different reaction, table 2 shows the value of the rate constant at different temperatures. So we've got all the data here for temperature and rate constant for 2 experiments. We've been given this dirty equation, which looks like the Arrhenius equation. And we need to find EA, which is the activation energy. So you've got to rearrange that equation to find EA that's on the right there. So what I'm going to do is first of all simplify by carrying out ln K1 divided by K2. So I want to do 1.55 times 10 to the minus 5, which is K1 in our data table, and divide it by 1.7 times 10 to the minus 14. And if you do that, you're going to get ln 0.0912. Now, I want to get rid of the ln. I basically want to carry that out, and I'm going to get minus 2.39 once you do ln 0.0912 on your scientific calculator. So now I can simplify the equation and write that equals EA over 8.31, which is what R is, multiplied by 1 over T2 minus 1 over T1. So let's simplify it by going 1 over 333 minus 1 over 303. And if we pop that into the calculator and simplify that, we can turn that into one number that's easier to deal with. So let's do 1 over 33 minus 1 over 303. So we're going to get minus 239 equals EA over R, which is 8.31, multiplied by minus 2.97 times 10 to the minus 4. Now, I want to bring that minus 2.97 times 10 to the minus 4 over to the left, and I can do that by dividing both sides by that. So I'm going to end up with minus 2.39 divided by minus 2.97 times 10 to the minus 4, and that is going to equal EA divided by 8.31. Now, you should be thinking about, how do I get rid of the 8.31 to leave EA on its own? Well, we're going to multiply both sides by 8.31 because it's being divided. That will get rid of it to leave minus 2.39 divided by minus 2.97 times 10 to the minus 4 multiplied by 8.31, and that will give us the EA. And when we whack that into our calculator, we should come up with the answer of 66. Let me have a little look in the old scientific calculator. Bada bing, bada 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 boom. 66.87 kilojoules. You could round that to 1 dp if you want to. 66.9 kg. All right, hit the like, guys. Let's go. One more bit to do. Okay, 1.8. Name and outline a mechanism for the reaction of butanone with KCN, followed by dilute acids. Okay, so first of all, I'm going to do the mechanism because it's easier to do that than name the mechanism after. So I'm going to draw out butanone. 4 carbons. We need a carbonyl group somewhere on there. So there we go. The carbonyl group has either got to be on the second or third carbon, so it'll always be the second carbon, as it would be an aldehyde if it was on the other ends. Now I've got a nitrile group here with CN, lone pair. Draw the lone pair going to the carbon. Why does it go there? Because I've got delta positive. In AQA, you can just write plus and minus on the carbon and the oxygen here on the carbonyl group. But it's good practice to put a delta sign to mean it's slightly positive or slightly negative. Anyway, my nitrile group, the lone pair is attracted to the carbon. Therefore, the double bond to the oxygen must break because it needs to restore only having 4 bonds around the carbon. That will get you 2 marks for that on the mechanism. Now we're going to draw the intermediate. I'm using the skeletal formula just to show you you don't have to do displayed. You can do skeletal. So here's my oxygen. Where shall I put the... Oh, no, I'm going to put the oxygen at the top here. I'm going to flip it around a bit. I'm going to put the lone pair on the oxygen because the double bond broke and went to the oxygen, okay? Now, what's the lone pair going to do? It's going to be attracted to a hydrogen ion. What? You say, where did that hydrogen ion come from? Don't forget, it said we followed the addition of KCM with a dilute acid. Whenever you see hydrogen ions knocking about, an acid's been there. And then I need to draw the bond to the CN. Now what's going to happen, our final product is going to have a hydroxide group, an OH group or hydroxy group attached there, and a nitrile group at the bottom there. So just draw those bonds a little bit straighter on the skeletal. How do we name this? Well, it's called a hydroxynitrile. So you don't need to name it, by the way. That's not one of the marks. You get all 3 marks or all mechanism marks for the mechanism. So we don't need to name this. But if you wanted to name it, you'd count the carbons along 1, 2, 3, 4, and you'd say, it looks to me like 2-hydroxy butan nitrile. Butan 2-nitrile. So 2-hydroxy butan 2-nitrile. Now, what's the name of the mechanism? Well, it's going to be nucleophilic because the nitrile group with the lone pair is a nucleophile. It's attracted to positive things because of its lone pair. And it's going to be nucleophilic addition. How do we know it's addition? We know it's addition because there are 2 reactants, which I'll circle here in blue, and 1 product, which I've circled in orange. So when you have 2 reactants and 1 product, you know it's addition. And nucleophilic because of the nitrile. That's me done. Question 2. Tetrafluoroethene is made from chlorodifluoromethane in this reversible reaction. So we have 2 moles of chlorodifluoromethane, reversible symbol, and then we have 1 mole of tetrafluoroethene ethene plus 2 moles of hydrochloric acid or hydrogen chloride. And the enthalpy change is plus 128 kilojoule per mole to the minus 1, so that's endothermic. A 2 mole sample of CHClF2, that's the chlorodifluoromethane, is placed in a container with a volume of 23.2 decimeters and it's heated. When the equilibrium is reached, the mixture contains 0.270 moles of chlorodifluoromethane. That was the initial reactant. Okay, calculate the amount in moles of C2F4 and HCl in the final equilibrium mixture. Okay, I am going to rewrite out the equation, but I'm going to simplify it without the state symbols or the reversible symbol, just because I just want this for the purposes of this equation. This is going to help me with this calculation, basically. So I'm going to write this out. Now I'm going to make a little table some of you may have been familiar with. Different people write different things on the side of the table. So people do this when working out the amount of moles in an equilibrium mixture. They make a little grid like that of the products and reactants, and then I write I. So it tells us, which I've highlighted at the top, that we've got 2 moles of CHClF2, and we can't have any moles of the products yet. So no moles of C2F4 and 2HCl. So how much does it change by? Well, if you take the 2 moles that we have of the initial reactant, and then it tells us how much of the reactant is left afterwards, which is 0.270 moles. So let's do 2 minus 0.270, and that is going to give us the amount that those moles changed by. And the answer, of course, is going to be 0.173 moles. So what happened is, of our 2 moles of initial reactant, 1.73, moles were used up, leaving behind 0.270 moles. Now, as the ratio of our reactant to our first product is 2:1, it means we only get half the amount of moles used up or created, of the product. So we go 1.73 divided by 2, because the ratio is 2:1, we get 0.865. So at equilibrium, we have 0.865 moles of the first product. Now we look at the relationship between the reactant and the final product, the second product, the HCl. We find that it's 1:1. So as we used up 1.73 moles of the reactant, it means we produced 1.73 moles of the product, the HCl. So the amount of tetrafluoroethene is 0.865 moles, and the amount of hydrogen chloride is 1.73 moles. Okay, let's move on to 2.2. So what do we have here? Well, I'm reusing the equation here, and it says give an expression for Kc for this equilibrium. Excuse the fact I don't have state symbols or a reversible symbol in my equation. So when you're writing out Kc, you just need to think products over reactants. So let's write down the products. Now we need to put them in brackets, square brackets, because that stands for concentration. So those square brackets mean mole per dm to the -3, so it saves you having to write that out. Now I put a little 2 outside the HCl. Why do I do that? That is because there are 2 moles of it, so it's to the power of 2. And for the bottom, the product, CHClF, we put a little 2 outside as well, and that's your equilibrium expression for Kc. Okay guys, don't forget to pause the video and have a go at these. So 2.3, calculate a value for Kc. So what we need to do here is just simply plug the units in. So 0.865, that was the moles of C2F4. And if we look back at the original stem of the question, or are working out to the first part, 1.73 were the moles we worked out for HCl. And the moles of our reactant at equilibrium was 0.270. Now I'm putting the little sign for the power of 2 outside because there were 2 moles of it. Now, something that we've also got to take into account is that in the stem of the question, it told us that we had 23.2 decimeters. And it said right here in the stem of the question that these were placed in a container with a volume of 23.2 decimeters. So we need to make sure that we divide the moles by the decimeters to get the concentration, and then we square the results for the ones we need to square. And if you do that, you're going to get the answer of 1.53, but now you need to work out the relevant units. And as you can see, there are mole to the dm to the minus 3, mole to the dm to the minus 3 on the. And this is because I have 1.73 to the 2. So there's 2 mole to the dm minus 3s. And just with below, I have 0.270 to the 2. So I have 2 mole to the dm minus 3 there, which makes my units, because those all cancel out, mole to the dm minus 3. And so there's our answer, 1.53 mole per decimeter. 2 marks, or 3 marks, with the working out. Okay, for 2.4, state and explain the effect of using a higher temperature on the equilibrium yield of tetrafluoroethene. I suggest you pause the video, have a go. Okay, I'm writing out the equation here again with the reversible symbol and the gaseous symbols. We actually don't need the gaseous symbols for this because we're not talking about pressure, which is where you look at how many moles of gas are formed on each side of the reversible symbol. We're actually more interested in the delta H, the enthalpy of this reaction. And it's plus 128 kilojoule per mole. And that tells us it's an endothermic reaction. So what's the effect on yield if you increase the temperature? Well, if you increase the temperature, the yield's going to increase. But why? That's because the forward reaction is endothermic. You see the plus 128? So the forward reaction is endothermic. Remember, if you increase the temperature, our reaction, the equilibrium will shift to oppose the change you've made. Remember, that's Chatelier's principle. And that means the equilibrium will try and oppose the change. And so to oppose your change of increasing the temperature, it forces it to the side that takes in energy, the endothermic side, which is the right-hand side. And that's why the equilibrium shifts in the forward direction and we get a higher yield. So your 3 marks here are 1 for stating the effect on yield, which is that it will increase, 1 for saying the equilibrium will shift to oppose the change, and finally that it shifts, therefore, in the forward direction. Chemists provided evidence that was used to support a ban on the use of chlorodifluoromethane as a refrigerant. Many refrigerators now use pentane as a refrigerant. State the environmental problem that chlorodifluoromethane can cause. Give one reason why pentane does not cause this problem. Well, that's a CFC, and so we know it destroys the ozone layer and breaks down or contributes to the depletion of ozone in the ozone layer, thinning it or making holes in the ozone layer, which is pretty dangerous because it lets ultraviolet radiation, the dangerous ultraviolet radiation, through. So why does pentane, as I'm drawing out here again, but a second time, why does this not cause the problem? And it's to do with a particular bond that you don't find in pentane. So what makes chlorodifluoromethane dangerous is the CCl bond, and of course pentane doesn't have a CCl bond. So it doesn't form free radicals that break down the ozone layer. And that's your answer. This question is about 2-methyl-but-1-ene. Name the mechanism for the reaction of 2-methyl-but-1-ene with concentrated sulfuric acid. Outline the mechanism for this reaction to form the major product. And give the name of the mechanism, and this is worth 5 marks. Now, there is another step to this mechanism which they don't require here, which is if you add cold water, you actually end up with an alcohol, but that is not included in the stem here. So we just need to do the first part of this mechanism, and we need to write out the structure of 2-methyl-but-1-ene first. I know I've got a bit of a dodgy methyl group attached there, but I just couldn't really draw it with the writing properly. Okay, so we've got concentrated sulfuric acid, so I need to draw the structure of sulfuric acid next. Sulfuric acid here, obviously, H2SO4. So I just want to make sure I get the structure right. And it's a structure that you need to learn off by heart because it's got those 2 double bonds. It's a slightly unusual structure. And just check you've done 1 sulfur atom, 4 oxygens and 2 hydrogens. And it's remembering the structure of sulfuric acid that actually makes this mechanism one of the hardest ones for alkenes. Okay, so we've got a slightly positive charge on the hydrogen atom and a slightly negative charge on the oxygen atom on the sulfuric acid. And of course, that means that this electron-rich region of the double bond is attracted to that slightly positive hydrogen, so 2 electrons move over to form a bond with the hydrogen. Now, as hydrogen can only form one bond, it has to break this bond that it has with the oxygen on the sulfuric acid. Now, there are two possibilities here of the carbocation, the intermediate that can form. Now, you don't need to write these in the mechanism, but I'm going to go through with them just so you can see what the two possibilities are. And it does come in later in the question. It will help us out anyway. So I'm going to do that on the side here. And I'm going to call these two carbocations, which are the intermediates, A and B. So in the first one, I'm drawing carbocation A. I've had the hydrogen join the first carbon with the double bond. So we can see the hydrogen is attached here, which I've circled in blue, and it's attached to that carbon. Okay, now this that's the hydrogen there, circled in green, that has attached, and the other carbon now only has 3 bonds and has a positive charge, and this is the carbocation, this whole intermediate. Now we have a second carbocation that can form, and this is if the hydrogen instead joins to the carbon atom, the other carbon atom, leaving the carbocation leaving the positive charge on the first carbon. So we're going to draw out this formula as well for the alternative carbocation. Notice I put CH3 there. I can't fit in drawing out all the bonds. And so let's put the hydrogen here. And we're going to put a positive charge on this first carbon. And actually, there's a rule called Markovnikov's rule that can help you realize where the hydrogen atom goes. But I might do a video about that at a later date, as it's a rule that nobody uses anymore, really. Okay. So which of these is more likely to actually form? Well, going to put a little note up there. Haven't been able to fit that in. So this first product, I'm going to circle these 3 groups here. These are called alkyl groups. So A is the major product because it forms more of these alkyl groups, and these are electron releasing, and they stabilize the positive charge. And so that intermediate is more likely to form because it is more electrically stable or energetically stable. The minor product, product B, the carbocation there, is less likely to form. Now, why is this important? It means that it affects our final molecule. So now we're going to get on and finish the mechanism using the carbocation A. We're not going to use carbocation B, so I'm going to draw out carbocation A again down here. Okay, God, it's a pain in the backside. Right, let's draw this out. Just copy the one above. Okay, I'll do the C's and the H's properly this time. Oh, I can't fit this in. Okay, there we go. So that is the more likely carbocation. Again, it has 3 alkyl groups or more electron donating groups that stabilize it. Now I'm going to draw the hydrogen sulfate ion. That's what you call a sulfuric acid that has lost a hydrogen, a sulfuric acid molecule that's lost a hydrogen atom. So it has a lone pair and a minus sign on the oxygen because going back to the original draw, the first step of the mechanism, it received 2 electrons with that orange arrow from the OH bond. So now it has a lone pair of electrons. And this hydrogen sulfate ion is going to be attracted now to the positive charge on the carbocation, and those 2 electrons are going to form a bond with the carbon. And that's the end of the mechanism. So the mechanism itself will score you 4 marks. 1 for each of the orange arrows and the positive and negative sign on the sulfuric acid over there. And then we're going to get 1 for the carbocation correctly drawn and 1 for the orange arrow going from the lone pair and the minus sign to the carbocation. So 4 marks for the mechanism. Now we need to name this mechanism. And if you have if you have 2 reactants and 1 product, and we've got 2 reactants here at the start, and we're going to end up with 1 product once our hydrogen sulfate ion joins to our carbocation, it's going to be addition, and it's electrophilic addition. The reason being because the positive charge on the sulfuric acid is attracted to the electron dense region. It seeks out that electron dense region. So it's an electrophile. And so this is electrophilic addition. And that is the typical mechanism that all alkenes undergo, is electrophilic addition. And you only need this bit that I've circled in green. That's what you needed for your answer. You didn't really need to draw out all the carbocations. All right, let's move on. Again, like always, you might want to pause the video and have a go. So draw the structure of the minor product formed in the reaction in question 3.1. Explain why this is the minor product. So to draw the minor product, I need to draw my carbocation B, which you can rewind back a little bit if you want to have a look at it. And this is the carbocation, the minor carbocation that's least likely to form. So this was the one where it didn't have many alkyl groups. And so I put the positive charge on the first carbon. Now that's going to be attacked by that hydrogen sulfate ion. So all I need to do is join the hydrogen sulfite ion here. So I'm going to get rid of the positive charge, and then I'm going to attach the sulfuric acid minus the hydrogen because it's a hydrogen sulfate ion. And I'm going to draw the attachment here. And this is the minor product. Now, if you want to name this minor product, this is an alkyl hydrogen sulfate. And it's going to be 2-methyl, because we've got that methyl group on the second carbon, butan, because there's 4 carbons in the straight chain there, 2-iyl. 2-methyl, butan, 2-iyl, hydrogen sulfate. Forgot to name the hydrogen sulfate. Geez, that's a serious name. You don't have to name that. Let's just forget about that, yeah? Right, the major product has more alcohol groups which are electron donating, so forms a more stable carbocation. So our explanation is the reason why this doesn't form is because the major product is more stable. It has more electron donating groups, so it forms the more stable carbocation, and that will get you the 2 marks. You could write it in the reverse way and say the minor product has less alkyl groups, so less electrons released to stabilize it, so less likely to form. Anyway, that will score you 3 marks, 1 for the drawing, 2 for the explanation. Let's move on. So we're on to 3.3. Draw the skeletal formula of a functional group isomer, of 2-methyl-butanene. So what is 2-methyl-butanene? Which homologous series does it belong to? Well, you see the ENE, so it's an alkene. Can you remember the general formula for alkenes? CnH2n. And that means that we can work out its molecular formula. It's got 5 carbons, so it's going to be C5H10. And that means I just need to think of an alkane with the formula C5H10, because that will be a different functional group. It won't have the C double bond, the carbon-carbon double bond. And these cycloalkanes are the perfect functional group isomers of any alkene. So we just, cyclopentane is what we're going to write here. Now, if I had propene, I would have cyclopropane. Okay. So it doesn't contain the double bond. That's why we say it is a functional group isomer. Let's move on to 3.4, because that was just a 1 marker. So 3.4, 2-methyl-butanene can form a polymer. State the type of polymerization. Draw the repeating unit for the polymer formed. Type of polymerization. Now, you did this in GCSE, so we've identified already that we're dealing with an alkene, which contains a functional group that's a carbon-carbon double bond. And you should know from GCSE, alkenes undergo addition polymerization. Oh, I don't know. Have I spelled undergo? Is there an E on the end of undergo? No, I think it's right. Oh my gosh, I can't spell addition. Never mind. All right. Anyway, yeah, alkenes undergo addition polymerization. So the type of polymerization is addition. The other type that you can put as an answer is condensation, but you get a water molecule removed there. Okay, so now let's draw the repeat unit. So in order to draw the repeat unit, I want to do the monomer. I want to write out 2-methyl-butanene again, but in kind of monomer form. So we got the double bond here, and then I'm going to draw it all out like this. Okay, so how will I make this into a polymer? There's a very simple formula to follow. Just copy the double bond over to your repeat unit. So we're going to copy the double bond over. You do this in pencil. Then add the groups onto the carbons. Leave an open ends. Those 2 lines are open, and put the brackets through them straight away. Now I just need to take the hydrogens and add them on here from the first carbon. You're literally just transferring over all the groups. The tricky bit comes on the second carbon. Also, I've got 5 carbons around there. You can't have 5 bonds around a carbon atom. So remove one of those bonds, keep that as a single bond now. And now what we're going to do is add the groups over. So I've got a methyl group here, and the tricky bit now is taking this C2H5 that I'm circling in pink. This is an ethyl group, and bending this down below the carbon. Okay, so your repeat unit can only ever have 2 carbons in the brackets. Everything else needs to be above and below. Oh my gosh, you shouldn't write CH2, CH3 like that. Okay, I'm going to put C2H5, but you could write CH2, CH3, which is our ethyl group. Just don't write it how I did, which was a bit weird. And that's question 4. Proteins are polymers made from amino acids. Part of the structure of a protein is shown. We've got cis, asp, and fer. These are abbreviations for amino acid names. Each amino acid in the protein is shown using the first 3 letters of its name. Identify the type of protein structure shown. So we have 3 possible answers, which are primary, secondary, and tertiary. The primary is the amino acid sequence. The secondary is the first level of folding. You've got beta pleated sheets or alpha helix. And then you've got the tertiary structure. Oh my gosh, I can't spell. Or 3D structure. Okay, you can see there what we're shown is a linear line of amino acids. It is the amino acid sequence, the sequence or order of the different amino acids. And that's the first answer, the primary structure. Now we're on 4.2. Draw a structure for the cis-ser section of the protein. Use the data book to help you answer this question. So now we need to flick to the data book and see if we can answer the question. So here's the data book, and you can see there's the structure of cysteine and there's the structure of serine. So I've circled those. Those 2 structures I'm going to draw out and then work out how they bond together. So this isn't going to score you any of the marks, but what I'm going to do now is draw out those structures. So the first one I'm going to draw out, okay, I'm just copying it down from the data book. I'm going to do this in a different color. And this is cysteine, which has the sulfur atom on it, on its R group. And the next one we're going to draw out is serine. It doesn't have the sulfur atom, but I'm going to draw this in blue because it's going to help us identify what's happening with the different atoms when these 2 join. Now, of course, they're going to join to form a dipeptide, but they could form a giant polymer, a polypeptide, by just joining end to end and end to end. And they form in condensation polymerization. And of course, condensation refers to the water molecule that's formed when 2 amino acids join together. So we're going to lose the hydrogen off the amino group and the OH off the carboxylic acid. And of course, you have to remember, which people don't, if you're doing a polymer rather than a dipeptide, then you lose another OH off the amino acid and another H off of the amine group. So it goes on and on and on. So for every 2 amino acids that join together, you get 2 H2O molecules produced. All right, let's join them together now that they are joined. So I'm redrawing these minus the atoms that I've circled above. You get no marks for the drawing I've originally done there of cysteine and serine. This is me just showing you the working out. But what we're going to do here is show the peptide link with the carbonyl bond and the NH bond joined together in the middle there. And we've lost the OH and the H from the middle. And don't forget, for your trailing ends, they're the lines that come out the brackets at either side. For your trailing ends, you need to remove an OH from the carboxyl group and an H from the amino group. And that is the answer. You can see it right there. That is what is formed when a cysteine and serine join together. And it's that will get you the 2 marks. Don't worry about the water molecule or the bit above this. That was just working out. Okay, 4.3. Name the other substance formed when 2 amino acids react together to form part of a protein chain. So we just saw that from my drawing before. You get a water molecule being released, and remember you get 2 water molecules, one from the middle and then one from either end, where you've got the other peptide chain, bonds forming. Right, the general structure of amino acid is shown. H2NCH with an R group. R represents a group that varies between different amino acids. R groups can interact and contribute to protein structure. 4.4. Explain why the strength of the interaction between 2 R groups differs from the strength of interaction between a serine R group and an aspartic acid R group. So we're going to go back to our data book here. So we go back to our data group and identify cysteine with the sulfur atom attached, and we've got the aspartic acid with the two carboxylic acids. The carboxylic acid is on the R group as well as the normal. So now we just want to look at why the strength of interaction between the two cysteine groups is different than the strength of interaction between the R groups on the aspartic acid. Now remember, the cysteine groups have these sulfur atoms, and what I've drawn here is a disulfide bridge that is across the middle. So now I'm going to draw the interaction between the two R groups on aspartic acid. Now remember, aspartic acid has an R group with a carboxylic acid on it. It has the carboxylic group in the normal amino acid structure, but in the R group it has an extra one. And what we have going on here is we have hydrogen bonding. So remember, oxygen is delta negative or partially negative, and the hydrogens are partially positive. And so what that results in is hydrogen bonding. So now we know that the aspartic acid has hydrogen bonding and the cysteine groups form disulfide bridges. We have to ask ourselves, which one is stronger? Well, cysteine groups form strong disulfide bridges. Now, disulfide bridges are a covalent bond of shared electrons. So you've got those strong electrostatic forces of attraction between nuclei and pairs of shared electrons. And that is going to be a lot stronger than the intermolecular force, that is hydrogen bonding, that we get formed in aspartic acid between the R groups. Okay, so really this is a 4 marker. You're going to get 1 mark for acknowledging that cysteine groups form disulfide bridges, 1 mark for acknowledging that disulfide bridges are covalent bonds, 1 mark for saying covalent bonds are stronger than hydrogen bonds formed in the aspartic acid groups. And that's your 4 marks. Boom. Sorry about my voice on today's video. There's something up with my audio. It's coming out like a robot. So we have 4.5. Deduce the type of interaction that occurs between a lysine R group and an aspartic acid R group. We need to go back to our data book and check it out. So if you look, we have aspartic acid. This has got the carboxylic acids, and lysine over here has got an amine group on the R group. So we've now got the interaction between a carboxylic acid and an amine group. Now let's have a little look at what goes on there. So I'm drawing out the amine group and the carboxylic group on the lysine and aspartic acid R groups that interact. What happens is one of the hydrogen ducks over to the amino group, making it have a positive charge, and the carboxylic acid ends up a carboxylate ion with a negative charge. And of course, positive and negative charge, these aren't partial. This forms ionic bonding. And that's your lot. So subscribe, hit the like, let's get to the marks. Question is about the preparation of hexane 2-ol. Hexane 2-ol does not mix with water, it's immiscible, essentially, and has a boiling point of 140 degrees. Hexane 2-ol can be prepared from hex 1-ene using this method. Measure out 11 centimeter cubed of hex 1-ene into a boiling tube in an ice bath. Carefully add 5 centimeter cubed of concentrated phosphoric acid to the hex 1-ene. After 5 minutes, add 10 centimeter cubed of distilled water to the mixture and transfer the boiling tube contents to a separating funnel. So you're looking to get rid of those impurities that are soluble. Shake the mixture, allow it to settle, discard the lower aqueous layer, add a fresh 10 centimeter cube sample of distilled water and repeat the steps D and E. Transfer the remaining liquid to a beaker, add 2 grams of anhydrous magnesium sulfate and allow it to stand for 5 minutes. Filter the mixture under reduced pressure, distill the filtrate and collect the distillate that boils in a range of 130 to 160 degrees. Let's get to the questions. 5.1. It's important to wear eye protection and a lab coat when completing this experiment. So we can't write those down as answers. Suggest with one reason another appropriate safety precaution for this experiment. Well, you remember we're using phosphoric acid. So wear gloves because phosphoric acid is corrosive. You also might want to use a fume cupboard. When you're dealing with organic solvents or organic chemicals or compounds, they're volatile. They vaporize easily and can form toxic fumes. So this should be done in a fume cupboard as well. Give a reason for adding the distilled water in steps C and F. So why do you add distilled water? Well, the distilled water will dissolve any soluble impurities, things that can dissolve in water. You can then get rid of the aqueous layer. So distilled water dissolves soluble impurities. That's your answer for 5.2. Let's look at 5.3. Make sure you pause the video before each of these and have a go. Give a reason for adding anhydrous magnesium sulfate in step H. What does anhydrous mean? It means without water, dry. So this is a drying agent. It's going to absorb water really well. So it's going to dry out your product and remove any of that distilled water that's left behind after it's been removed. So it's a drying agent. It removes water. Now we're on to 5.4. Complete and label the diagram of the apparatus that is used to filter the mixture under reduced pressure in step I. So you need to know about this apparatus for filtration. And the first thing we're going to add is a Buchner funnel, okay, which I've badly drawn here, and you'll score some marks for the labeling of this because it does say we need to label the apparatus, label the diagram. So you've got a Buchner funnel. A Buchner funnel naturally has a ceramic plate in it, but you also place moist filter paper in there as well, and then your solid is going to go on top of the moist filter paper. So you need to have, to get these marks, you need to have labeled the Buchner funnel, the moist filter paper, and put some sort of bung into the end of the pump, of the conical flask, sorry. And that's really all you need. And the solid just goes in above the filter paper. Don't draw like my solid I've done here. I've messed it up. It shouldn't be poking through the filter paper. So that's a bit of an error there. So don't worry about that. But what do you need for the marks? You need the Buchner funnel, some filter paper, and the bung, and all of them labeled. Identify the most likely inorganic impurity other than hexoneine in the distillate collected in step J. So obviously hexoneine was our starting reactant and hexan-2-ol was our product. Other than the leftover reactant that hasn't been got rid of, what's the other likely impurity? Remember, during electrophilic addition of alkenes, we can form two possible carbocations. This is the less stable one formed, and this is going to form hexan-1-ol as a minor product. Okay, so you're going to get some hexan-1-ol formed. I worry about my spelling of hexan-1-ol. There shouldn't be a hyphen between the hex and the "an" there. Sorry about that. Now, why is it difficult to separate hexan-1-ol from hexan-2-ol? Well, they've got the same mass. They're going to have the same type of hydrogen bonding because of the alcohol group. So they've got a similar boiling point, same physical properties, similar boiling point. So very difficult to separate from each other by distillation. Okay, let's look at 5.6. Calculate the mass in grams of hexan-2-ol formed from 11 centimeter cubed of hex-1-ene if the yield is 31%. Give the answer to one decimal place, and we know the density of hex-1-ene is 0.678 gram per centimeter cubed. So you're going to need the density calculation. You should be triggered by seeing the density word there. So D equals M over V. You're also going to need the yield calculation. So we want actual mass over theoretical mass times 100 equals the yield. And here they've actually given us the yield, but we're missing that actual mass, and that's what we want to. We want to basically find the actual mass. So the first thing to do is work out our mass of hex-1-ene that we have. So we're going to use the 11 centimeter cubed and the 0.678 gram per centimeter, whack it into the density calculation to do density times volume, and that's going to give us the mass of 7.458 grams. Now turn the mass of hex-1-ene into moles. So you're going to use your mole equation, which is mass over mR times moles. So you need to find the mR of hex-1-ene. So it's going to be C6H12. And if you add that up, that's 6 times 12 plus 12, you're going to get 84. And if you divide your mass by 84, you're going to get 0.088785 moles. I put an N for number of moles. Now there's a 1-to-1 ratio between the reactant, which is the hex-1-ene, and the hexan-2-ol. So that means if we have 0.088785 moles, we should get the exact same amount of hexan-2-ol. So we should have 0.088785 moles of hexan-2-ol as well, in theory, if everything has gone perfect with our experiment. So Now we want to find out exactly what mass that will be. That's going to be our theoretical mass. So we're going to do 0.088785. We're going to stick it in the mass equation. By timesing that by the MR, we're going to work out the mass. Now the MR of hexane 2O is going to be C6H14O. Okay, and we're going to get 9.056 grams because the MR is 102, so we times the moles by 102, we get 9.056. So we've just worked out the theoretical mass and we know the yield, so we just need to rearrange that equation to work out the actual mass. So 31% is going to be equal to the actual mass over 9.056 times 100. Of course, you can divide both sides by 100. Personally, when you're timesing by a percentage, you know 31% is 0.31. So we're just going to do 0.31 times the theoretical mass, which is 9.056, and you get your answer, which is the actual mass. So 0.31 times 9.056 grams, you're going to get 2.807 grams. We're going to lose a mark unless we check this here, 1 decimal place. It's always easy to miss that, so you should use a highlighter. So it's 2.8 grams to 1 dp, and that'll get you 4 marks. Boom. This question is an organic analysis. This question is about compound X with the empirical formula C2H4O. Figure 2 shows the infrared spectrum of X. Figure 3 shows the C13 NMR spectrum of X. And the H1 NMR spectrum of X shows 4 peaks. Look at the table 3, you'll see those 4 peaks down below. It's got the chemical shift, the splitting pattern, and integration values. So what we've got to do is use all of this data, including the empirical formula, to identify compound X. So your job here is to piece together and find out what compound X is using the IR spectrum, all the wavelengths, the CNMR in the second bit of data, and in the third bit of data, the NMR. So show how the information from Figure 2, Figure 3, and Table 3 can be used to deduce the structure of compound X. Essentially, you're going to get 5 marks for using the data from the left-hand side there, and 1 mark for the final structure. So this is probably the hardest thing in the whole of A-Level Chemistry to do, organic analysis. You can still get 5 out of 6 without coming up with the correct final structure. But I'm going to show you how you can piece it all together, although it's pretty difficult to do on video like this, but let's go. So I recommend you pause the video, have a go, using an AQA chemical insert with the data table. You can just Google that to get all the relevant data. And here we go. So first of all, we're going to look at the infrared spectrum of X. What we're going to notice from this infrared spectrum is that we have a broad peak at 3,400 to 3,400 and 500, sorry, and this must be an OH bond. And you can see that from the wave number and the bond here on the data table. Now, it's not going to be the NH because the empirical formula doesn't contain nitrogen. So you can see it's C2H4O and there's no nitrogen, so it can't be the NH bond. Now there is a second peak at 1680 to 1750, and we can see that this, not that, it's the COO. And I'm just trying to go through here and get all the points down because you're going to get like 2 marks for talking about the infrared spectrum, and you can get 5 out of 6 for just talking about how to work out the structure, even if you can't piece it together at the end. But we now know that it's likely to contain an OH bond and a carbonyl group as well, the C double bond O. So now the next thing to look at is the carbon NMR, C13 NMR. And we can see from the table we've got there is a chemical shift at 20 to 50, and that tells us that the carbon in that environment has a carbonyl group attached. This confirms that we're dealing with a carbonyl group. So we know that from our figure 3 here, we can see there are 4 carbon environments, and we know that one of them between 20 to 50 contains a carbonyl group. So this is confirming what we found out in the infrared spectroscopy, that we have that carbonyl group, the C double bond O. Now let's look at one of the other peaks in the CNMR13. And again at figure 3, we'll see one of the other peaks is between 70 and 75 as a chemical shift. And what we'll find when we go to the AQA chemistry insert is that between 50 and 90, so that covers the 70 to 75, there is a CO bond that will be an alcohol or an ether or an ester. And here it's going to be an alcohol. We've got a CO, and remember we had a COOH from the um, we had a COH from the infrared spectroscopy. So that pieces it all together that we're probably dealing with an alcohol as well. And another of the peaks at 210 looks like it's going to be a ketone when we look at the data table. So we've now got it kind of confirmed in our minds that we've got a carbonyl group separate to a hydroxy group, not joined together as in a carboxylic acid. So now when we look at the HNMR spectrum, which we've got a little table at the bottom, we'll find there's a peak at 3.99 chemical shift. We'll find that it has an integration trace of 1, meaning there's only one hydrogen in this environment. So you need to write that down, and that will get you a mark. And you also need to say that it's a quartet. And what does the quartet tell us? It tells us that the adjacent carbon has a CH3 group. So that shift at 3.9 tells us we're dealing with this here. So we've got one hydrogen with the integration trace. We're dealing with a C to the O bond, but we know that the adjacent environment has 3 hydrogens. So now we're going to build this section of the molecule. We know there's an R group connected to an O. We know the carbon had 1 hydrogen. There's our CH there. But we know that as it was a quartet, the adjacent carbon had a CH3, a methyl group attached. And we need to write that down. So we're looking at COH. This is our environment, but the quartet tells us there's a methyl group attached. If you put that information down, you're going to score more marks. Let's look at the next part of the chemical shift. So at 3.7, we have an integration trace of 1, meaning there's 1 hydrogen in the environment. But when we look at the data table, we can also see the structure here. So we've got this hydrogen here, and it says there's only 1 hydrogen in that environment, and it's connected to a C and an O. So we're looking at this group here circled again, and as it is a singlet, it means there's a carbon environment attached or another adjacent environment with no hydrogens. So we can presume this. The adjacent carbon that I've drawn here has a carbonyl group and therefore no hydrogens attached. So that could be what is attached to this COH. So you just need to point out what the singlet tells you, that the neighboring environment has no hydrogens attached. Now I'm going to need to use this side of the board as well as I'm running out of room. We have another chemical shift at 2.1. We need to point out the integration trace is 3, which means that this represents a hydrogen in an environment with 3 hydrogens. So we're looking at the methyl group here. And this shows us that we're looking at our hydrogen being a methyl right here. So 3 hydrogens there. And it's attached to a carbonyl. So we've got a methyl group attached to a carbonyl. And we can find that from the 2.1 trace. The integration told us that there's 3 hydrogens. And the chemical shift told us that it's attached to a carbonyl. So from what we pieced together earlier, it would make sense that this group with the carbonyl and the methyl attached, I've circled in blue here, would be attached to that earlier group we confirmed. And what could the missing R be? Well, we know there's an OH, so maybe that's a hydrogen. Let's check out the chemical shift at 1.2 now. And 1.2, we know has a methyl group because it has an integration trace of 3. So it's another methyl group. And we know that it's a doublet, which means there's one H attached on the adjacent carbon. And we can see from this. So this information is really confirming what we found earlier here circled in yellow, that we got a methyl with a carbon with 1 hydrogen attached. Okay, and we can look here with the chemical shift to find that it definitely was a methyl group. So that integration trace told us there were 3 hydrogens, and the fact that it's a doublet Well, that means there's a carbon attached, which I'm drawing here in brown with one hydrogen off of it. And of course, we already had this earlier from our IR spec. So now we need to just put together everything we know, which I'm doing here in blue. We know we've got a C with three H's, a CH coming off of it, and an O. That's probably going to be a hydrogen coming off of that O. And we know we've also got a carbonyl group coming off as well, which we worked out from earlier. So we know this is probably an H there from the OH from the IR. And then coming off of this carbon, we know we learned from the 2.1 integration trace that there's going to be a carbon atom attached to a carbonyl group and with a methyl group attached. So that is probably our final structure. So when we piece all of our information together, we know we have a methyl with a carbon with one hydrogen attached. We know we have a carbonyl group coming off of that and another methyl group coming off of that. And we're also expecting to have a hydroxy group coming off of that. Another confirmation to this structure is that if we check the empirical formula, we'll find that the empirical formula is actually or our molecular formula here is a multiple of the empirical formula, which helps too. So you can see it was C2H4O, our empirical formula, and this one that we've drawn has C4H8O2. So it's a multiple of that, and it's further confirmation we've got the correct structure. But as I say, setting out your working out will get you 5 marks, and the final structure, which you piece together with a bit of detective work, will get you that 6th mark. If you're going for an A star, you can do that by getting 5 out of 6 for explaining all the data. With plenty of exam practice at NMR and organic analysis, you can become an expert on these very difficult questions. I'm going to make lots more videos on these because these are the hardest ones and hopefully some better ones, but this is just part of an overall exam pack. So, yeah. Figure 4 shows an incomplete mechanism for the reaction of an ester with aqueous sodium hydroxide. Here we've got figure 4, and we have step 1, step 2, and step 3. You can see it shows arrows here, transfer of electrons shown through curly arrows. And if we look at the first question, it's 7.1. It says add 3 curly arrows to complete the mechanism in figure 4. So looking at this first diagram, we can see carbon is supposed to only have 4 bonds around it. Well, a maximum of 4 bonds. And if this was to actually form bonds here, we'd end up with 5 bonds. So if this OH group is going to donate an electron pair to the carbon, it means that carbonyl double bond is going to have to break to allow there to be only 4 bonds. Of course, that then donates some electrons to the oxygen. And that gets you your first mark for that curly arrow. Now, the second curly arrow, we've got this step here. You can see this intermediate. Again, 4 bonds. 1, 2, 3, 4. So what's going to happen? Well, the oxygen with the lone pair is redonating its electrons to form the carbonyl bond again. That would be 5 bonds again. We need to snap a bond off. But which bond do we snap off? That's the big question. Which of these bonds should go? It's actually this bond here. Now, how do we know it's this bond that's going to break off? Well, if we look here circled in blue, we can see what the result of the breaking of the bond is. So it has to be that bond there that's breaking. And of course, it gains a lone pair of electrons, that oxygen, so it would match perfectly with what I've circled in pink here. Now we need to show another bond, another curly arrow, and another movement of electrons. We can see here that the hydrogen is forming a bond with that oxygen. The lone pair is going from the oxygen with the negative sign to the hydrogen. Now, hydrogen can only have one bond, so it can't continue to be bonded to the O, the oxygen, and form a new bond with the oxygen with the lone pair. So what does it do? It separates and breaks itself away from the oxygen here, and we can draw a curly arrow to show that. It's going to donate its electrons back there, and that makes sense because when we look at the step down below, we can see that the oxygen atom attached to the carbon with the carbonyl group has a negative sign over here circled in pink. So we can see that these two match up perfectly. So that's where the bond and that's where the pair of electrons end up. Okay, that's your 3 marks for the 3 curly arrows. Now name the type of reaction shown. Well, this reaction is base hydrolysis or hydrolysis, however you like to say it. Why is it hydrolysis? Well, look, I've got one product. I'm going to circle it in blue here. One reactant, sorry. I've got one reactant and 2 products. So there's been splitting, and lysis means to break. Now, why is it base hydrolysis? Look here what I've circled in blue. That gained a hydrogen, and when you gain a proton, you are acting as a base. So that's why we call it base hydrolysis. Now 7.3, deduce the role of the CH3O minus ion in step 3 shown in figure 4. So let's go back up there and have a little look. If I circle it there, the CH3O minus ion, what is its role? We just discussed this. What atom is it gaining? Well, look what it's sending its lone pair on the O minus 2. It's sending it to the hydrogen. So it's gaining an H plus ion, because technically that's going to snap off and become an H plus ion before it joins to that lone pair. So when you gain a hydrogen ion, what are you? You're a base. So it's accepting a hydrogen, therefore it is acting as a base. Brilliant. When you're a base, you're a proton acceptor. Let's look a little bit closer before we do the final question, which is a 1 marker. Let's look a little bit closer at this base hydrolysis. So this is an ester that I'm drawing here, and this is a nice simple ester. It's methyl and propanoate. So it's come from methanol and propanoic acid formed in a condensation reaction. Methyl propanoate. It's an ester. Ester link there in the middle. Now we can hydrolyze this ester link. We can break this ester linkage, and with a hydrolysis reaction with water under acidic conditions, and we're going to form methanol and propanoic acid. So methyl propanoate is broken into methanol and propanoic acid, and I've drawn in blue where the hydrogen, the oxygen have ended up. Now let's look at base hydrolysis, which is slightly different. So we're going to look at base hydrolysis now. So what I'm doing now is I'm going to draw another ester. This ester is a very large ester, a triester. Okay, involves 3 separate esters all bonded together, and it's an ester like we find in vegetable oil. Now this has got CH2 16 times, so a really long side chain coming off the carboxylic acid part of the ester. And if we use sodium hydroxide, which is a base, we're going to need 3 of them because it's a triester, so we need to break 3 ester links. And this is called base hydrolysis. And essentially, we're going to split this into an alcohol. Now, this alcohol is going to be glycerol, otherwise known as propan 1,2,3 triol. But instead of getting a carboxylic acid like we make with the acid hydrolysis, we're going to get a carboxylate ion, sodium carboxylate. And the difference is that the hydrogen atom on the carboxylic acid on the left is replaced with a sodium ion, an Na plus ion. So this hydrogen I've circled in yellow is going to be replaced with an Na plus. Okay, so you still get an alcohol, although it's a triol, but this time you get a sodium carboxylate instead of a carboxylic acid. And there it is. And this sodium carboxylate is actually a salt, which is soap. So for the final question, a triester in vegetable oil reacts with sodium hydroxide in a similar way. We've just looked at that reaction. Give a use of the product. Well, it's the sodium carboxylate and it's used as soap. There we go. Let's get to the marks. We're looking at the electrophilic substitution of benzene involving a halogen carrier. This is question 8 of the AQA Chemistry Paper 2, 2022. Give an equation for the overall reaction when benzene reacts with methanoyl chloride. Name the organic product. We need to write an equation and give the name. And it's worth 2 marks. So first of all, let's look at methanoyl chloride. What is it? Well, it's an acyl chloride. And they're basically a carboxylic acid, but you swap the hydrogen for a chlorine atom. So as it's meth, it's only got 1 carbon. We draw the carbonyl group with the double O bond and the chlorine atom and the hydrogen. Now the other reactant is benzene, which I've drawn here in green. Remember, benzene has the formula C6H6. There are 6 hydrogens attached to 1 to each point on the benzene. So first of all, we want to write out the reactants. So HCOCl plus C6H6. Now, what happens next? Well, we need to write out the products. And electrophilic substitution, as it's in the title, is what most benzene molecules undergo. They undergo electrophilic substitution. This helps them retain the delocalized ring. If you try and do addition, you've got to break the ring, or elimination, you've got to break the ring, and it tends to be very stable. So we've substituted the aldehyde group from the methanol chloride, the COH, onto the ring in place of a hydrogen that you can see is joined with the chlorine from the methanol chloride. And so that's why it's electrophilic substitution. The hydrogen has been taken out and swapped places for the aldehyde group, and the chlorine atom from the acyl chloride has joined with that hydrogen that got taken off of the outside of the ring. All right, now what is the name of this? Well, it involves benzene, and we've got an aldehyde group, the COH. So you can call this benzaldehyde. However, some people like to see the benzene ring as a side group, and you're looking at methanal as the most basic aldehyde. COH is methanal, and so they see the phenyl as the side group, so phenyl methanal. Either will get you the marks. 8.2, identify the catalyst needed in this reaction. Give an equation to show how the catalyst is used to form the electrophile HCO plus, with the plus outside the brackets. Okay, well, the catalyst we use is called a halogen carrier. And the most common one to remember and to memorize is AlCl3. And here we have our methanol chloride, and it can be made into an extremely strong electrophile by removing that chlorine atom, leaving a positive charge on the carbon, making it attracted to electron-dense regions like the delocalized ring in benzene. So the equation for this is HCOCl, which is methanol chloride, plus the halogen carrier AlCl3. And what happens is the chlorine is snapped off of the methanol chloride and added to the halogen carrier, which becomes AlCl4 minus. I've added a plus to my electrophile, and I've put it above the carbon, but you could put the plus outside of the brackets to the top right, just like you would with an ion, and that will get you 2 marks. Right, now for the final bit, 8.3, we're going to outline the mechanism for the reaction of benzene with the electrophile. So I'm going to draw my benzene ring in green here first. And now this is being attacked by HCO plus, which is our electrophile. So we've got C, double bond O with an H coming off, and then we have a positive charge on the carbon. Now notice I've drawn a curly arrow going from the ring because it's electrons that move, not positive charge. You can't draw a straight arrow, that won't get you the marks. And so that's coming from the ring, I'm touching the ring and going to the carbon atom. And it's a pair of electrons that represents. Now I'm redrawing benzene here, although this is a bit crusty. Let me just make that a bit simpler. There we go, that's a bit better. And now we need to show that the ring has been broken because it's lost a pair of electrons. We mustn't, I've drawn this dotted line here, we mustn't extend our horseshoe shape beyond carbon 6 and carbon 2. It mustn't extend beyond that, as you won't get the mark for the horseshoe.
Don't forget that there are hydrogens attached in the intermediate, because there's one at each point of a benzene ring. And don't forget you need a positive sign inside the broken horseshoe, which shows that the delocalized ring has temporarily broken. Now, in order to restabilize the ring, the hydrogen will break off by donating its pair of electrons to the ring to reform the delocalized ring, and the hydrogen will become a hydrogen ion. So now we draw the reformed ring. By this time, we've got the aldehyde group attached. You don't normally have to draw the final product of mechanisms unless stated, but sometimes it's good to anyway. Sometimes, rarely on the mark scheme, they give you a mark for the final product. They just want the mechanism, but it's worth doing it sometimes. So there we go. That's your mechanism for the outline of benzene with an electrophile. And you get 3 marks for that. Super.
This question is about olive oil. So let's get into it. A sample of olive oil is mainly the unsaturated fat Y mixed with a small amount of inert impurity. The structure of Y in the olive oil is shown. Y has the molecular formula C57H100O6. The MR is 880. The amount of Y which is found by measuring how much bromine water is decolorized by a sample of oil using this method. Transfer a weighed sample of oil to a 250 centimeter cube volumetric flask and make up to the mark with an inert organic solvent. Titrate 25 centimeter cube samples of the olive oil solution with 0.025 mole per decimeter bromine aqueous solution. A suitable target titer for the titration is 30 centimeters of 0.025 mole per decimeter bromine solution. A suitable target titer for the titration is 30 centimeter cubed of 0.025 mole decimeter bromine solution. Already said that. Justify why a smaller target titer would not be appropriate. Calculate the amount in moles of bromine in the target titer. Okay. So our target titer has 30 centimeters. So if we want to work out the percentage error, let's say the error is 1. We're going to do 1 over 30 times 100. And that's going to give us a percentage error of roughly 3.3%. Let's just make that up. Okay, this is just for illustration purposes only. Now let's say we only used a 10 centimeter target titer, 10 centimeter cubed. Well, it'd be 1 over 10 times 100. We'd get a 10% error. So the larger your target titer, the smaller your percentage error. So if we use a smaller titer, this is going to lead to a higher percentage error or level of uncertainty in the answer. And there we go. That's for 1 mark. That justifies the larger titer. Now the second part, we need to calculate the amount in moles of bromine in the target titer. So let's get down to this. You remember the equation, obviously, which is moles, N, I like to use as moles, over CV, concentration times volume. Well, they've given us the volume, 30 centimeters. We need to turn that into decimeters by dividing by 1,000. And they've given us the concentration, 0.025 mole per decimeter. So if I times the volume by the concentration, I'm going to get the moles. 7.5 times 10 to the minus 4 moles of bromine is what we have in the target titer. Okay, here comes a difficult calculation. Calculate a suitable mass of olive oil to transfer to the volumetric flask using your answer to 9.1 and the structure of Y. Assume the olive oil contains only 85% of Y by mass. If you are unable to calculate the amount of bromine in the target titer, you should assume it is 6.25 times 10 to the minus 4 moles. This is not the correct amount. Okay, if we take a look at the stem of the question, we can see that the ratio of bromine to Y must be 5 to 1. And this is because there are 5 double bonds in the structure of Y. Look here, I've circled them. Okay, that means you're going to need 5 bromine molecules for every one of these Y molecules. So the ratio is 5 to 1. So we're trying to find a suitable mass of Y to add. So we want the mass of Y. So we're going to have to use our formula, which is mass over MR times moles. And do you remember from step 9.1, we found out there were 7.5 times 10 to the minus 4 moles of bromine. Well, that means because it's in a 5 to 1 ratio with Y, we divide by 5, we have 1.5 times 10 to the minus 4 moles of Y. Now that we know the moles, we score a mark for that, we now need to work out the mass. And we can do that by using the MR and putting it into our moles, mass, and MR equation. So if we look at the MR of Y, we can see it's 880 from the stem of the question here. And then all we need to do is put our moles, mass triangle down like this. Find out the MR of Y, which we've just said from the stem is 880. Use our moles, multiply it by 880, which is the MR, and we'll end up with the mass of olive oil, or the mass of the molecule Y that's in the olive oil. And that's going to give us 0.132 grams, but remember that's the mass that's found in only 25 centimeter cubed. If we look at the stem of the question again, we can see that they took 25 centimeter cube samples of olive oil out of 250 centimeter cubed. So we need to multiply by 10 to get it back to the original. So now we know in the original 250 centimeter cubed, there was 1.32 grams of molecule Y. So now we know that, we just need to find out how much olive oil we would need to put into the volumetric flask. Remember, the olive oil isn't 100% molecule Y. It only contains 85% of it by mass molecule Y. So we're actually going to need more olive oil than we have the mass of Y, because only 85% of the olive oil is Y. So what we're going to do here is 1.32 grams divided by 85 to find what 1% of the olive oil is, times 100. We're going to get 1.55 grams of olive oil. And there you go. That's your 5 marks for part 9.2, which was probably the hardest part of this question 9 of the 2022 paper. Let's move on. All right, 9.3. The olive oil solution can be prepared using this method. Place a weighing bottle on a balance and record the mass in grams to 2 decimal places. Add olive oil to the weighing bottle until a suitable mass has been added. Record the mass of the weighing bottle and the olive oil. Pour the olive oil into a 250 centimeter cube volumetric flask. Add organic solvent to the volumetric flask until it is made up to the mark. Place a stopper in the flask and invert the flask several times. Suggest an extra step to ensure the mass of the olive oil in the solution is recorded accurately. Justify your suggestion. So we need an extra step here. You see, they poured the olive oil into the volumetric flask, but they didn't reweigh the weighing bottle afterwards. They should have reweighed the weighing bottle after, subtracted the mass, and then find out the mass of olive oil that they actually added. So they may think that they put 5 grams of olive oil into the weighing bottle, but actually you need to reweigh the weighing bottle after and find out how much olive oil was actually entered into the volumetric flask. And the reason is so that we can calculate the mass of olive oil added accurately. Now we need to know for 9.4, state the reason for inverting, that means turning the flask upside down, inverting the flask several times. And the reason is we want all the contents to be evenly mixed. We want the moles of all the different contents within that solution to be mixed evenly. And this can be described as being homogeneous or uniform. So you can say to ensure the contents are evenly mixed, but if you want to get funky, you can say to ensure the solution is uniform or homogeneous. Okay, final part, 9.5. A sample of the olive oil was dissolved in methanol, placed in a mass spectrometer. The sample was ionized using electrospray ionization. Each molecule gained a hydrogen ion, H+. During ionization, the spectrum showed a peak for an ion with an MZ of 345 formed from an impurity in the olive oil. The ion with MZ345 was formed with a compound with the empirical formula C5H10O. Deduce the molecular formula of this compound and show your work. Okay, so we need the molecular formula of this compound. Well, we're going to need the MR, and 345 is the MZ ratio, which is equivalent to the MR. However, it had a hydrogen ion added because it was electrospray ionization. So to find the MR, we need to do 345 minus that hydrogen ion, which has a mass of 1 because it's a proton, equals 344. So 344 is the MR of our impurity. Now, we've been given the empirical formula, which is C5H10O. So we need to add these up. So we've got 5 times 12 for the carbon. That gives us 60, plus 10 is 70, plus 16 for the oxygen is 86. So kind of like the mass of the empirical formula would be 86. We know that the molecule has a mass of 344 from the molecular mass. So we do 344 divided by 86. We know that there is a difference of 4 is the factor difference. So we need to multiply the empirical formula by 4 to get C20H40O4. And that is the molecular formula because it's 4 times bigger than the empirical one. Awesome. There's your marks. End of the question. Hit the like. Question 10. This question is about the reaction scheme shown. You can see here we've got a reaction scheme with methylbenzene. We've got step 1 going to toluidine, then we've got step 2, then we've got step 3, we've got step 4 where we've got free radical substitution, and then step 5 we've got amine B and amine A. 10.1, state the reagents needed for step 1 and the reagents needed for step 2. So for step 1 we're nitrating the benzene, so we're getting that NO2, that nitrate, onto the benzene. And how do we do that? We use concentrated sulfuric acid, and we need nitric acid as well. And we're going to have a little look at this rather than just have the answer. I'm going to explain the mechanism for this as well. And for step 2, this is going to be reduction, and we're going to do this with tin, the metal tin that is, and concentrated HCl. That should be concentrated HCl. So let's have a little look at the mechanism for this step 1. So we have sulfuric acid, and you mix that with nitric acid, as those are the reagents for step 1, concentrated. And what we get is a 2-step reaction, and we're doing all of this so that we can form some sort of positive electrophile to attack the ring. And here it is, the NO2 with the plus. We end up with H3O plus. Oh, missed out one thing at the top here. Let me just fix that up. We've got a sulfate ion there as well, hydrogen sulfate. Let me just rewrite that out there. Yeah, so we've got 2 hydrogen sulfate ions there. Now, of course, at the end of this reaction, you'll see that the sulfuric acid is a catalyst because it gets reformed. So it goes to a hydrogen sulfate ion in that reaction to make the NO plus. When they get a lone pair, well, we get electrons moving from the ring to the nitrogen to form a bond. Obviously, this breaks the ring. You can't extend beyond the points on the benzene. So, and yeah, then the sulfate ion is going to join with that hydrogen that has to snap off of the intermediate by donating its electrons to reform the broken benzene ring. And we end up with NO2. And that's why this is a catalyst here. This is just a little bit of extra waffle. But your answer really was sulfuric acid and nitric acid. And then we got the reduction with tin and hydrochloric acid for step 2. And that has to be refluxed. And then you add sodium hydroxide for that one as well. But the mark scheme just needs you to say tin and concentrated hydrochloric acid. Okay, let's look at 10.2. Give the name of the mechanism for the reaction in step 3. Okay, so we're going to look at the mechanism. And the name of the mechanism is nucleophilic, although you don't need that in the mark scheme. It's nucleophilic addition elimination. So it's an addition elimination reaction, but you could, if you're going to call it electrophilic or nucleophilic, you call it nucleophilic addition elimination. And it's this reaction here to form this molecule here. So we're going from this amine A over here. Okay, so we're looking at the mechanism here. So I've got a benzene ring with a methyl group, and I've got an amine group attached. The amine has a lone pair on the nitrogen, and now I'm drawing an acyl chloride in pink, and this has got a delta negative on the oxygen and a delta positive on the carbon. The lone pair is attracted to the delta positive on the carbon. Carbon can't have 4 bonds, so the oxygen has to break one of those double bonds, and then we get the intermediate. And the intermediate has a nitronium ion. It's basically a nitrogen with 4 bonds with a positive, just like you get in ammonium. That's going to want to reform, and the chlorine is going to break off, which will allow the oxygen lone pair to reform the double bond on the carbon. And one of the hydrogens has to break off to stabilize that positive nitrogen. So we're going to end up with a chlorine atom and a nitrogen atom eliminated. So we've got our addition in the first step, which was the pink acyl chloride molecule joining to the phenylamine, the methyl phenylamine, whatever, and that's addition. And now we've got elimination with this hydrogen and chlorine breaking off to form hydrogen chloride. So it's addition, elimination. And it could be called nucleophilic addition because the lone pair on the nitrogen
Okay, state a
was
necessary
a
condition
nucleophile.
for step 4. Well, the reagent's chlorine and the condition is ultraviolet light. We're going from an alkane, like methobenzene here, and we're doing free radical substitution to form a halogenoalkane, like chloromethobenzene at the end of step 4. Now, amine A is formed in step 2 and amine B is formed in step 5. Explain why the yield of B in step 5 is less than the yield of amine A in step 2. Well, let's have a little look. So we've got amine A at the top here. Now, what the question's saying is this is in a higher yield. This ends up, we produce a lot more of this than we do when we do step 5 to produce amine B, which we get a lower yield. Explain why that is. Okay, so let's go back down to the question. And it's a 2-mark question. So essentially, step 2 only forms one amine. That's why we get the higher yield. Whereas step 4 can form multiple different amines. Now, I'm going to look into the details of that to explain why.
So I've got my halogenoalkane. Now, if you react these with excess ammonia, you make an amine. Okay, and this is step 4. This isn't step 2. This is the one with the low yield. So you react this with excess ammonia, and you end up with this molecule here. And this product is a primary amine. You can see the 2 hydrogens on the nitrogen. So it's primary. It's also got a lone pair on the nitrogen. What does this mean? This means if we have excess halogenoalkane, more of the reactant there, it's going to re-react with the product, with the primary amine, because the lone pair will be donated to the delta positive carbon. The chlorine will snap off, and one of the hydrogens on the amine will snap off to form hydrogen chloride. But you can see there, you're going to get a secondary amine. And then you can further react that to get a tertiary amine or a quaternary ammonium salt.
Okay, 10.5. Explain why amine B is a stronger base than amine A. So what we're looking at here, we have amine B, and this is the better base. Now what happens is it has a CH2 group or an alkyl group that is donating an electron pair, making the lone pair more available. Okay. Whereas when we look at amine A, which is not as strong base, not as good base, it's got this methyl group here, but the nitrogen is directly attached to the ring. And what happens here is the lone pair on the nitrogen, which it would normally like to donate to the hydrogen, is less available because this arrow shows it's being drawn into the delocalized ring. Okay, so we say it's being partially delocalized, the lone pair. Now you can answer this with amine B is a stronger base, this has an alkyl group, electron donating, makes the lone pair more available, and that will get you 2 marks. Or we can argue it, amine A is a weaker base, has less alkyl groups, or we can say the nitrogen directly attached to the ring. Benzene is electron withdrawing, so the lone pair is partially delocalized or less available on amine A. And there we go. That'll get you 2 marks too.
You're still here? It's over.